Hi guys, welcome to the 10th lecture on model-driven engineering and model-assisted software development. So with the previous lecture, we introduced MASD as a methodology. We described the different aspects of the methodology and so on. What I'd like to do now is to look specifically at Dogen, which is the tool that embodies MASD and really was the originator of all of the ideas that we now see in my thesis and so on. So what we'll do is this is not so much a lecture as a walk through the code really. I think it's important to do that because a lot of the theoretical discussions that we've had so far in these previous 10 lectures, they're very difficult to make sense of without, especially if you're a software engineer, without background in model-driven engineering. They're difficult to make sense of unless you've got something concrete in terms of code, unless you start to see classes and files and things like that. So I think it's important to understand that before we progress, before I conclude. That is, this is the last, or the last, or the one before last lecture in this series. So as I mentioned before, Dogen. Let's just quickly jump over to excuse me, the website. So Dogen is a regular project in GitHub. In fact, the top level project is MASD project, where you'd find the reference products, C Sharp, C++, some experiments, but the main project really is Dogen. And what you see in Dogen is a regular C++ project, I guess, with sort of a structure that you expect from most projects. But the interesting thing, of course, is that the structure of Dogen is defined by MASD, as I explained in the previous lecture. Notions such as component collections and components and so on, those are instances. What you see here is an instantiation of the MASD architecture. And in fact, it is this instantiation and the observation of this instantiation that gave rise to the structure that we described in the previous lecture. So I think the best way to understand the way Dogen works is to have a quick look at the logical model, because the logical model is the center of the activity inside of Dogen. It probably doesn't make a lot of sense to look at the logical model in isolation, but hopefully what we'll do is we'll join the dots just to make sure we understand the pipeline. And the idea basically is that we have, I'm using before we continue, I'm using an old representation of Dogen, which is now part of Frozen. In other words, we moved away from Dia. We don't use Dia anymore. But the diagrams in Dia are much higher quality than the PlantUML diagrams because we are not finished with PlantUML yet. So if I look at that very same diagram, a more up-to-date version of that diagram in PlantUML, which is this guy here, as you can see, we are lacking relationships between elements, and they're all just flat. There's a few of them, to be fair. Inheritance, for example, is here, but we are lacking a lot of these relationships, which makes the diagrams much more difficult to understand. If you look at zoomed in version of it, I mean, all the data is still here, but without the relationships that we've got in Dia, the classes just become they're all over the place, which makes it really difficult to make sense of the information here. So what we'll do instead is we'll just go back in time to a few releases ago. I think it's just one or two releases ago, so we're not too far off mainline. And we'll look at the nice manual Dia representation we used to have, and just to give us the overview of the architecture. So, like I said, Dogen is made up of a number of components. You can see those components in where was I? Missing a Emacs window somewhere. Did we close it by mistake? Oh, there it is. Oh, it's just underneath the Dia window. Excuse me. Maybe I'll just move it to a different desktop so we don't get confused. Dogen is made up of a number of components. Each component is a shared library, with the exception, or a static library, with the exception of the CLI, which is the driver. We probably should really convert these to shared libraries, and we will at some point. We just haven't done that yet. We haven't really spent a lot of time coding since the last release. In fact, we haven't spent any time coding since the last release, which was, let's have a look, beginning of the year, if I'm not wrong. Yeah, so literally the first few days of the year, where we did this change to move from dia to org mode. That was the last release we did. The reason why that was the last release is because we didn't really want to. No one really enjoys writing a thesis. I don't think it's a lot of hard work. I mean, just to give you an example, this is one of the first drafts of the thesis that contains pretty much all the material, and you can see it's pretty hefty. Um, that contains both the notes as well as all the papers. And whilst I've been writing this over a long period of time, it still was not very pleasant to get everything together and work through the logic and check all the papers and so on. So the only way to do that really was to ensure that I didn't spend any time coding, which I find fun. I just was not allowed to do any coding until I finished all the paperwork. And now with this series of lectures and with the Vive on Friday, that hopefully will be the end of that cycle. And with the end of that cycle, we'll go back to coding again. There's still a lot of coding to be done, but the fundamental principles are all there, which is a good thing. So as I was saying, you can think of Dogen as a pipeline, and the pipeline takes a model from an input representation such as JSON or DIA or org, and for that we have the codec subsystem, and then we transform that representation over to the logical representation, where a lot of the hard work is done in terms of transforms. And what you can see here is the transform chains for the logical model. I'll cover these in detail in a second. In some detail, probably not all the detail, but and then of course once we finished going through all these transforms and we have a completely parsed logical model, we then take that logical model to a physical representation. Sorry, the dog is gnawing. A bit difficult to concentrate in this place. So as I was saying, we take this representation from the logical model, the logical representation, over to the physical representation. And in the physical representation, which as I've mentioned in the previous lecture, it's important not to confuse the physical representation with the actual files in the file system. But the physical representation eventually will have the notion of something that looks like a file in memory, and that something is an artifact. And then we will write that artifact over to the file system. Now, when I said that there's lots of coding to be done, this is a classic case of that. So when we were doing the theoretical work, we concluded that actually there are two types of artifacts: file artifacts and directory artifacts. And the modeling in the physical model is still not updated to reflect that. And there's also limitations in the way that relations between files are done and so on. There's quite a lot of updating that needs to be done. The theoretical model has been finalized with the thesis, but the code representation is still slightly out of sync. It's not huge amounts, but it's just slightly out of sync. And then, of course, there's a whole lot of features that we want to add now that we finished all the theoretical work. So once we got a physical representation, once all the processing has been done, we eventually write the artifacts over to the file system as files. And that's kind of the end of the processing. So if we take the codec representation as an example, my dia is misbehaving a bit. You see here different elements in this diagram with different colors. Those colors are significant. We used, I don't think I've got this handy. Oh, I do have actually. Inspired by a book on modeling, which I'll reference in the show notes, Java Modeling in Color. So these guys here, Code, Lefebvre, and De Luca, they explain the power of color in trying to convey information in the diagram, and it's actually really well written, that book. But the gist of it, really, the long and short of it, is that if you start to create metatypes and associate those metatypes with color, it's much easier to parse the diagram visually, because the color starts to your brain processes a color and adds a different dimension to the diagram. So in Dogen's case, we find it very easy to look at the diagram with color because we now know what the metatypes mean. So if I look at something with this color, I know it's going to be a comment. If I look at something with this color, I know it's a registrar for serialization. Um, and if I look at this color, I know that's a regular Poco or Pojo, whatever you want to call it, a simple object, um, and so on. And of course, the palette for the colors, it's not specified. Um, it's not usually specified really. We've got a palette and it works. It's very basic. It's a first draft, I think, of the ideas around that. I don't think it's the best. And in fact, we need to reread the book I just mentioned to see if we can copy some of their ideas, because I think there's some research required in determining the best palette. But so it's sufficient for the purposes of the moment. So, like I said, there's a number of meta types available in Dogen. The object template is one such meta type. It enables you to define what in C++ you'd call a concept, I guess. Um, it's an object that doesn't really get, it's a meta object that won't get instantiated. And you can compose these meta objects in any way you like. But eventually, you're probably going to get to a root meta object. And this root meta object is, in effect, inheriting all the properties from these other meta objects. And then you instantiate that meta object by stereotyping it against another object, in this case attributes. What that does is it copies across all of the properties of the different meta objects, object templates in this case. um, and this is something we found very powerful in Dogen, because a lot of times we can think of objects as having a set of abilities, and those abilities are quite nicely described by object templates, and then you can just retarget those abilities to different kinds of objects. For instance, you can create an ability called commentable, which is this guy here. In other words, the ability to have a comment, and then you can just tag objects as required. For example, object is commentable. Interestingly enough, object is not an element. Not entirely sure why. This is probably historical, I suspect, if we look at the latest version of this. Probably shouldn't get too sidetracked here, but if I have a quick look for the very same object in this more recent representation, now you can see why it's so much harder to look for things here. You can do a search, to be fair. It's not incredibly useful. Right, here we are. Oh, I think we were in the codec model. There we are. Yeah, it's interesting. Object is just commentable rather than an element. Not entirely sure what that is. Let's just put a note in our release, in our sprint. So investigate why codec object is commentable. Most other types are. Let's just make sure we use the notation for. So we just have a note here to investigate this later. But really, this ability to define these meta types is really useful because it helps with the modeling process, because you start to subdivide the object functionality, well, not so much the functionality, but the structure of an object into a series of substructures, and then you start to think of those substructures separately. And then the good thing about this, of course, is if you are using generic programming, as you probably would be in C++, you can make use of this analysis in your code, because you can then create these concepts as C++ concepts. Now, Dogen doesn't have support for that at present, but in the future, we will write this. We will generate the concepts according to the latest C++ 20, I believe, syntax, which will mean that the code generator will then integrate meta model with the C++ meta model, which should be quite nice. But you can see here we have a very, very trivial model. All of this that you're seeing here is structural variability. In other words, we're just defining a set of structures with their own shape. And within the structural variability, you can see the different attributes that are defined for each of these objects. The objective of the codec model is to try to capture the minimal set of modeling elements the simplest possible way. And then we construct a chain that is able to process input formats over to this neutral model. So, for instance, I'm not entirely sure where we are in terms of. Oh, yeah. So for instance, this transform here, model to JSON, is able to take a JSON artifact and transforms that over to a codec model. And this transform takes org artifact. In fact, to be honest, this is the other way around. These transforms take the model and generate JSON. There will be an equivalent transform that goes the other way, which will be called JSON to model somewhere. So JSON artifact to model, and presumably die artifact to model, and org to model. And all these transforms are input formats that we support in the codec model. The original intention for Dogen was to have lots and lots and lots of these transforms, supporting things like XMI and so on. And we still think that this is going to be something that's useful, because the different one of the things we want to support was pervasive integration, as you remember from the previous lecture. And the idea being that each developer's got their own preferred format and their own way of working with things. So somebody may prefer perhaps a ideal like representation, such as the protobuf representation, perhaps, assuming that's sufficient to encode all the information required to generate a Dogen model. And in that case, you just go here and you add another transform that is able to parse the protobuf IDL and generate one of these guys. I'm just using that as an example. I'm not sure if that's very likely or not. However, what was interesting about the history of Dogen was that for many, many years, we just used the die representation that you see here. And that was quite sufficient. But in the end, we ended up moving over to org. And you can see a series of videos on how that was done. The reason why we ended up moving to org is because we bumped into the idea of literate modeling. And literate modeling is similar to the Knuth ideas of literate coding. And the idea is that you want to make the model as descriptive as possible to humans. This goes back to our discussions of Wittgenstein in W2 versus W1 and so on. Every model represents two things simultaneously. It has W2 representation, which is a language game designed to be played amongst software engineers and domain experts. And that normally tends to happen in natural language. And that's why you see all these notes and you see all these bits of information scattered across the UML diagram. But also, the other aspect of the model is that it is also a W1 artifact, in the sense that it is going to be transformed over to a source code representation, which will be used by the compiler to generate a binary, which will then execute. Afraid the dog is gone again. Not exactly the easiest environment to think in, but as I was saying, in fact, I lost the train of thought slightly. So the codec model is used to capture these ideas. No, in fact, we were discussing how we moved away. Oh yes, the W1, W2. Yes. So as I was saying, each model has this dual nature, this dichotomy between representing something that contains information for other humans via W2 and language games, as well as containing information for the compiler in W1. And what we concluded in the end was that the UML representation is very good to preserve elements of the W1 nature. It's a very formal representation, and it's really designed for transformations from a graphical representation over to source code. And it's really useful, of course. We really use UML diagrams quite a lot. That's why we always spend a lot of time keeping these up to date. But what we also noticed is that the contents of the model via domain-driven design and development, and via this approach that we keep on discussing, the language games, the most important aspect, or very significant aspect of the diagram, the model, is not the graphical representation, it's the textual representation. This is what we conclude in the end. What we really want is for the model to become the source of a written document, in effect. Let's see if I can explain this by example. So if I just make this slightly larger. So our conclusion was that we it's more important to be able to flip between a graphical representation and a textual representation that is designed for editing than it is to just have a graphical representation. The reason being that with a textual representation, um, we can edit just like any other file. So going back to what we discussed in terms of integration, our main workflow is in Emacs and is coding in Emacs, and we spend almost all of our time in Emacs. And having a tool like a Dia in order to see the graphical representation and to manage the graphical representation actually added a lot of friction to our development process. So we spent time going backwards and forwards between Dia and Emacs. And the more we thought about it, well, the more we understood that actually that was not, it wasn't a feature, it was a bug. We did need the graphical representation, but we need to look at the graphical representation to make sense of the structure of the code. But when we were managing the diagram, really what we wanted was the traditional functionality in Emacs. We wanted just the ability to select an area of text, copy and paste that area of text, um, use Emacs macros and so on to generate the text. Because at the end of the day, it was more about the natural language that it was about the, it was more about W2 than it was about W1 in effect. And also, of course, once you are in Emacs and once you've got something like org mode, the next logical thing you can do is you can use org mode's facilities, such as the export, and you can easily create, say, a PDF for a given model. Now, this is really important because the more you go towards literate modeling, the more you go towards Evans, the more you start to think, actually, I want to to use the model as a document. So if I just open up this guy, so as you can see here, what I've done there is I just using Emacs facility. I mean, this is all default, so of course this doesn't look very pretty, but using Emacs facilities, I just generated a PDF with the contents of that model. And of course, this is a very basic representation of it. But the future will be that the model will generate multiple outputs, such as um, the PDF representation, the plant.uml representation, and even the HTML representation, which is used as maybe to generate a website for the model. Uh, and so that all of the knowledge, all the W2 knowledge is encoded within the model, and we target different representations, whether those are W2 representations such as this one, or W1 representations such as source code. Org mode enables us to do all of that without having to worry about the machinery to do that because it's all built in. As you can see, there's already a plant.uml representation here, which we are generating at present. But all this to say what? We moved away from Dia into org mode, and it was a really very big gain. It wasn't just a quantitative change; it was a qualitative change. Modeling improved dramatically by making by doing this change because it is much easier to edit the models and to process and to think in terms of the models via the org mode representation than it was via the dia representation. The only slight downside is that we don't have the ability to supply all of the information that we had in the diagrams, such as associations, for instance. But we've got a good grasp of how to do that. So hopefully that'll be quite easy to do. And then the next release will probably not the next sprint, but the sprint after. Not the current sprint, but the sprint after. We will look into how to implement that. And this then means that our focus on allowing lots and lots of different codecs has slightly died a little bit. Because now, the way we're looking into it is, it's probably easier to just have a single codec. Um, that codec may even be XMI. I mean, we have got some literature on the topic. I haven't actually had the time to parse this properly. But if there was a standard-ish way that could be targeted by any tool, and that standard-ish way could, for example, be used to convert from an org mode um, document over to XMI, we could perhaps add the plugin to Emacs. As you can see here, there's a list of all the plugins that Emacs supports, which is quite a few. Um, And maybe if we did have that, I mean, let me just show you. This may not be obvious why this is so useful. So what I'll do is I'll just do another export. A second ago we exported to PDF, and hopefully that was obvious, the power of doing that very quickly. But nothing stops us from exporting to something else, such as HTML. And you can see here the diagram is now represented as HTML, and that there's multiple themes you can apply to these exports. So that is really useful, and so maybe in this world, really, what we want to do is we want to create a module in Emacs, extend this functionality here, and have export to XMI, and then have everybody else export to XMI as well, which is a very simple XML-based format. In theory, we haven't actually spent time investigating that. But if it is, and then that would allow us to remove all of the org-specific functionality in Emacs, as well as all the DIA and JSON and all of this stuff. We would remove that, and we would pass the task to generate XMI to the external tools. I mean, we could probably still support simple tools, maybe a tiny little command line tool that just generates XMI from multiple input formats. But maybe these things will not be actually Dogen things. This will be a separate project within Mazd that does the generation of XMI. And the reason why we'd want to do that is because we don't want to take on more code than we need to. I mean, Dogen is a development team of one, and you can imagine that potentially you could end up with a very large set of codecs in different shapes and at different levels of maintenance. And so if that's the case, we don't really want Dogen to be affected by that potentially um, varying quality of code. So that's the direction we're going. But originally, that's what we wanted. We wanted Codec to be a model that was not exposing too much of the internals of Dogen, so that we can bind it to other tools. And here you can also see how the terminology of MD is used throughout Dogen. So these are chains. They're made up of a set of transforms. However, because we didn't use any MD libraries such as EMF, this is all implemented as plain, straightforward C++ code. So in theory, if you open up any of these files, I'll just quickly jump over to the codec model. And if I just open up a transform, for instance, configuration transform, it's probably quite a trivial one. Let's make it a bit bigger so you can see. So you can see here, it's a transform is just a C++ class, very, very simple. Contains a transform context, and it just takes a model and then does something to it. In this particular case, we are looking for binding points, and for each binding point, we seem to create a configuration, which is this guy here. And all this code is regular C++ code, which makes it really easy to debug. It's fairly performant. It doesn't really have, I mean, it's not super performant, but it's not too slow either. It doesn't have any dependencies, which is very important. So it just runs as a simple standalone tool. Let's double check where we are in terms of time. Yeah, half an hour. So that's the codec model. Once we read one of these models, such as the org model, over to this codec representation, we then pass it over to a logical representation. We didn't really want to bind each of these models to each other. So what we've done instead is we created some elements. So if I look here, we need to bridge basically between the two. And in fact, I think in the end we updated this. Let's have a quick look because I haven't seen this code for a while. I think we may have actually added a transform, presumably in the pre-assembly chain. I think we've added a transform to read from codec model over to the logical model. Can't quite remember where that went. Oh, in fact, I think what we've did is, so if I just go up one level to the orchestration model, yes, to avoid having to introduce dependencies between all the different models, what we did instead is we created a higher level model, which is the orchestration model, and that model is responsible for binding the different parts of the pipeline. So, for instance, we have a codec model set to logical input model set. And then eventually there'll be a codec model to logical model. So the transforms that convert from one type to another are all encoded inside of the orchestration model, which is the model that has dependencies across the board. But then each of these individual models is independent. Um, we could have implemented Dogen as a graph and some kind of data flow like architecture. That would have been the right thing to do. However, Dogen evolved over time, over many, many releases, over 120 releases. And we tried to keep the number of dependencies to the minimum because in the beginning it was really hard to pick dependencies up. Now it's much easier because we use VC package, so we can get C++ libraries quite easily. But in the beginning it was quite hard. And we were supporting 3 different platforms, which made it really difficult to build for all these platforms. Now it's because of VC package and the cross-platform support we have in GitHub. It's actually quite easy. Um, so maybe in the future we will consider a data flow library. If we could set up the graph of transforms as a data flow library, we would be able to support parallelism much better. So we could just create dependencies between transforms and fire it off with multiple threads. We wouldn't even know about the threads. We just describe the relationships between the transforms, and it would be very easy to do that. This is something that's on the backlog, but not something we're going to work on next. I don't think. So yeah, as I explained, the orchestration chain is a high-level transform that orchestrates between all the different models within Dogen, and it is from here that you can see things such as going from the codec model over to the logical model, and then via the text model to a physical representation, and then from the physical representation over to files. This is what this chain here is orchestrating. Um, we still have some legacy things that need to be removed, and this is also part of the cleanup work that needs to be done. But once we exited the codec model and we entered the logical model, we have a much richer type definition. So all these elements, they were just described as elements. They get dispatched to the appropriate logical representation. And the logical representation is composed of a number of namespaces describing the different objects or meta objects, if you'd like. I mean, we just use the word object because everything will be meta, really. A number of objects on representing different domains. So, for instance, the structural variability domain is represented by these guys here. And we have things such as enumerations and objects, which is in effect a class, but because the names is a bit, we had to call it something else. Modules and so on. But these are just one of many, as you can see here. So, for example, we have the notion of decoration. So, if you remember, we described, and if I just go back to our presentation a second ago, if I can find it, presentation.org. So, we described, I'll just make this bigger, it doesn't really help. So, we described the taxonomical analysis that was done to break down files into their components. And those elements you see here, the decoration and so on, those elements are represented inside of the logical model, inside of the decoration namespace. As you can see, they're here. And these elements then get together to represent things such as the boilerplate, the preamble and postamble and so on. And like that, we have many other types. For example, our variability, and this is a non-structural variability. As well as aspect related to serialization, build types, and so on. The idea is that the library of patterns is encoded both on the logical level, as you can see here, as well as the template level, which is where the text model comes in. So within the text model, the job of the text model is to contain the model to text transforms, which take a logical representation and then convert that to the physical representation. And this model contains, in effect, the structure of the Dogen, the Maz project. So if you remember, I mentioned ideas like technical spaces, facets, and so on. Those ideas, those concepts, are baked into the actual infrastructure of Dogen. So you see here there's the meta type of backend, which really is not named correctly. It should be technical space. So in this case, we have C++ as a technical space. This is sort of reflecting back on itself because we are using Dogen to generate Dogen. So here we're defining a new technical space, and within that technical space, we define a set of facets, and those facets then have types. They then have elements, I guess you call it, or archetypes. And these archetypes are what you then will generate. So, for instance, a class header is an archetype, as well as a class implementation, and so on. And so the notion is that anyone can come over to a text model and they could create a new entity here, and that entity immediately gives rise to a new archetype. And when you create the archetype, you can then go to a model. Once you rebuild Dogen, you can go to a model, you can create an element and annotate it with that archetype. And immediately you'll be able to start co-generating that element. The properties that are available to you, of course, are the properties that are exist in the logical model. So if we go back to our text model, the modeling aspect of the text model, in here, if we look at the class header, which is very much this chap here, but in a much nicer representation, as you can imagine. Now it's trivial for me to look at the class header and look at the properties, because the properties themselves are just text. And via the magic of Emacs, I can edit the template in a specific mode for the template. There's a problem with my current version of Emacs, that's why you can't see the mode, but it would be here if it was available. And then when I'm finished, I just return back to my model. And with this, it's much easier to create new modeling elements. And once you create the new modeling elements, they're available for you to use on the next on your modeling process, which makes the iteration between modeling and well, the domain architecture to application transition much easier, because you could literally start by taking a paste of a file. You can put the file in here in the template. You can replace a few elements, and then you could just run the code generator, and you'd immediately generate that file, which makes it much easier in terms of developing the code generator. So that's the text, and then finally, of course, we have the physical representation, which in this particular case, it's largely describes the topology of physical space. So as you can imagine, there are elements such as facets and um, technical spaces and so on, and we need to know what elements are available. So this meta model, the physical meta model, contains all that information. The physical model then just contains the artifacts as they're ready to be written to the file system, which is the final stage before they get written. And so this is kind of the gist of Dogen, really. It's hard to explain without getting into a lot of detail in terms of the implementation level. It is very hard to explain how it works, because many of these concepts are all meta concepts, meta concepts, which makes it difficult to describe. So the best thing to do with Dogen really is to find a bit of the code that you need to change and just understand that area rather than try to understand the whole system. But at least this presentation should be helpful to describe how the pipeline works, so that at least you know where to look when you're looking for a specific feature. Um, I didn't even mention aspects such as variability and configuration. These are also complicated topics, but they are used quite a lot in Dogen. I'll just mention very briefly one example. So once we introduce some variability or some configuration point, um, say for instance, um, I don't know whether you force write or not. Um, by introducing this meta type feature bundle, this generates all the code necessary to create a feature in Dogen and exposes this to the diagrams, so that when you so in this particular case, let's have a quick look at what. Okay, it looks like Dia is not very happy, but this will introduce a new configuration point with the name such as mas dot something else. There we go. So in this case, we mas dot physical dot forced write, And you can then go over to the configuration of the model, and you can make use of that configuration point as soon as Dogen is built with that. So all of that is code generated, so you don't have to worry about anything. These are meta types; they're specific to Dogen. They enable you to configure Dogen, and that's very important. All of this infrastructure where Dogen is reflecting on Dogen is very important to the MAS approach, because that's exactly what we wanted to achieve, a system that was designed to develop a system. Um, and I think that a lot of these ideas will perhaps be applicable outside the world of AC and DSD. In other words, at the moment, we're only targeting architectural constructs, and there's lots and lots to be done on that domain. But one can imagine you could target other types of constructs, such as say a domain, such as say physical finance. So you could create a type called option, and then you can instantiate that, and that will then result in you generating code for I don't know, say Quantlib. Um, but I think that's something we will not do for a while. Right, I think we beat the records of interruptions and Dogen videos today. So yes, that's it. I think there is a possibility of targeting domains other than the architectural domain, but I don't think that's going to happen for a very long time. I suspect that's going to be a Dogen V3 probably sort of approach. Um, but the approach will be very much the same. We just introduce more logical model concepts. We probably would at that point have um, architecture centric namespace within the logical model, and then all of these entities will be inside of the architecture centric namespace, and then we'd have other domains such as finance and so on, and each of these will have their own namespace. Of course, in Dia that was not easy to do, but now that we've moved over to Emacs, that's really easy. All you need to do now is to take one of these guys here, and you can easily, using Emacs constructs, you can easily create namespaces and copy and paste and so on. So that's not going to be a massive issue, really. We'll be able to implement that quite quickly. Um, okay, I think that's pretty much it for this lecture. I mean, one thing we did not cover, we slightly ran out of time. I discussed very briefly that in MASD we had reference products, and what the reference products are, they are a way to seem to have some vulnerabilities. We need to update the C# project really. These projects reflect what the code generated looks like, and they're supposed to be an instantiation of each technical space. We are a little bit behind in these projects because the focus really has been on the code generator itself. They are used as sort of a compliance and conformance testing, um, but they are slightly out of date. For example, you can see that the models here are still using the dia representation, if I'm not wrong, and there's still a top-level directory called modeling models, in fact, that contains a different representation. So there's an overhaul that needs to be done here, which will be done once we conclude all the writing and the thesis work. And that's about it, really, for this session. I don't think there is scope for another session. Um, the other topic that we discussed in the thesis is literate modeling. So I think what we're probably going to do is we'll conclude this series of lectures here. I'm going to now work on a presentation that I'm going to do in my Viva, and I may make a session with just that presentation separately from everything else. But that's about it for this series of lectures, I think. Thanks for watching.